Hello, welcome to this lesson on Kirchhoff's first law. And despite the complicated sounding name, it's a very simple rule which helps us calculate the current in circuits. It was originally proposed by Gustav Kirchhoff in 1845. To help us understand it, let's take a look at, first of all, the top circuit here. We've got a cell, a bulb. Let's suppose we look at conventional current, which means considering the current going from the positive terminal round to the negative terminal. The current going into this bulb in the example is 0.7 amps, I subscript in. And the current leaving the bulb is also 0.7 amps. And the two values are always the same, whatever sort of bulb you use, whatever the circumstances. The current going in is equal to the current going out. Some people believe that bulbs on other devices use up current because they give off heat and light energy. Well, energy is not the same as current. Just because a bulb is giving off heat and light energy doesn't mean it's somehow or other using up current. The current that goes in is always exactly equal to the current that comes out. Always. And if we wanted to test that experimentally, we could put an ammeter on one side of the bulb and another ammeter on the other side, and the two ammeters would give the same reading. So, the current going into a device is the same as the current leaving it. It doesn't have to be a bulb. And the reason this is true is the law of conservation of charge. You may have heard of the law of conservation of energy, which says energy can't be created or destroyed. There is a law of conservation of charge, which says charge can't be created or destroyed. So whatever charge goes into a device leaves it. A slightly more complicated circuit. We've got a cell. We've got three bulbs in series. By in series, what we mean is that the things are connected so that whatever current goes into the first thing then goes into the second thing and then goes into the third thing. The current goes from one to the other. And you won't be surprised to learn that in this sort of circuit the current is the same everywhere. We could put ammeters at different points in the circuit if we wanted to check it, but in this example, if the current leaving the cell is 0.2 amps, then the currents at all the other parts of the circuit are also 0.2 amps, because we could pick any point in the circuit. It doesn't have to be the bulb. At any point the current going in is the same as the current going out, 0.2 amps. Let's look at components in parallel. Here we've got two bulbs in parallel. To keep it simple, we could have more than two in parallel. What do we mean by having components in parallel? It means that the current is going to be split. The leads from each component are joined at the junction. There's a junction on the top and a junction on the bottom. And the current comes along to the junction and splits so that some current goes down one component and the other current goes down the other component. And then at the bottom, the reverse is true. The current from the first bulb will meet the current from the second bulb and return to the cell. Look at the right-hand circuit diagram. I hope you see it's completely equivalent to the left-hand one. These two circuits are functionally the same. In the right-hand circuit, we still have current splitting some current through one bulb, the other remaining current through the other bulb, and then merging at the bottom and returning to the cell. So although they look different, these two circuits are equivalent, 100% equivalent. If we looked at the wiring, rather wobbly wires here, but these diagrams show two bulbs connected in parallel. In the first diagram, the connections are at the cell. In the second diagram, the connections are part way along the wires coming out of the cell. And in the bottom diagram, you can see clearly what's happening. Current is going to be splitting in two and then merging as it returns to the cell. So all of these things show two bulbs in parallel. Let's look at what happens to the current. Let's suppose 1.8 amps is leaving the cell and entering the top junction. Well, at the junction the current splits. Some is going to go down the first bulb, some is going to go down the second bulb, and if the bulbs aren't identical, we'll have unequal currents. Let's suppose that 0.8 amps goes down the first bulb. If that happened, we'd find that 1 amp goes down the second bulb. What's happening is that the current going into the junction, the 1.8 amps, is split. And the current leaving the junction has to add up to that 1.8. So the current leaving the junction in the example is 1 amp plus 0.8. So a total of 1 plus 0.8 is leaving the junction. 1.8 amps leaves and 1.8 amps goes in. It has to be that way. At the bottom the reverse happens. The 0.8 amps joins with the 1 amp and 1.8 amps leaves the bottom junction going back to the cell. So the current going into a junction is equal to the current leaving the junction. And this gives us one way of stating Kirchhoff's first law. The total current entering any point, it could be a junction, doesn't have to be, but the total current entering any point in a circuit equals the total current leaving it. Add the currents going in and they will equal the currents leaving. There's an alternative way of saying Kirchhoff's first law. To understand the alternative way, let's look at part of the circuit again, 3 wires at the top junction. What we're going to do is adopt a sign convention for the junction. If a current goes into the junction, we're going to say it has a positive value. So in this diagram, the current going in is 1.8 amps plus 1.8 amps. And we're going to say that currents leaving the junction have negative values. So this 1 amp current here we record as minus 1 amps because it's 1 amp leaving the junction. And similarly, the downwards current, the current value is 0.8 amps, but because it's leaving the junction, we say the current is minus 0.8 amps. If we add the currents together for this junction, we're going to get 1.8 plus minus 1 plus minus 0.8, and they must add up to 0 given what we've already said. And this sort of sum, where we take into account the direction of the current, whether it's going in or out, with a plus or minus sign, this sort of sum is referred to as an algebraic or vector sum of the currents. Vector is not a very good description, in fact, so it's best to call it the algebraic sum of the currents. And we can use this to state Kirchhoff's first law in a more formal way. Here it is. Kirchhoff's first law, the algebraic sum of the currents at any point in a circuit is 0. That's Kirchhoff's first law. For the mathematically inclined, we can express that in this form. You may or may not be familiar with the summation sign. This letter here is a capital letter sigma from the Greek alphabet, a capital sigma, and it means add together. And it means add together all the values of I, of current, the first current, plus the second current, plus the third current, till we get to the total number of currents. If there are 5 currents, capital N would be 5. If we expanded that, this symbology means I1 plus I2 plus I3, all the way up to the final current. And the currents add up to 0 if we use this convention of positive in, negative out. Let's use all that to see if we can do a simple calculation. Here's a circuit. We've got a network of resistors. So these two are in parallel with each other. These two are in series with each other. The first resistor has a current of 0.8 milliamps. The second has a current of 0.4 milliamps. The top resistor has 1 milliamp. I want to know what the current through this section of wire is at the top, I1, and what the current through this section of wire is at the top, I2. So if you want to pause the video for a moment and try and do this for yourself. Okay, well I hope you got the same answers as I'm showing on the screen. I've put the current directions in to help make the explanation a bit easier. Let's look at the junction on the top right. We know that the current leaving the junction is 1 milliamp and 0.4 milliamps, so the total leaving is 1.4. Therefore the total going into the junction is 1.4. I2 is 1.4 milliamps. What about the top left junction? Well, we know 1.4 milliamps is leaving it and 0.8 milliamps is leaving it. So the total leaving is 2.2. That means the total going into the junction must also be 2.2 milliamps. And if you want to check for yourself the current on the bottom, the currents match the top ones, 2.2, 1.4 and 1. Okay, I hope that's clear. Thanks for watching. Don't forget to learn about Kirchhoff's second law, which tells you how to deal with voltages in a circuit.